Question says, find the dimensions of the largest by area rectangle that can be inscribed in an isosceles triangle with base 12 inches and height 9 inches. Someone draw a picture, of course, because why wouldn't they draw a picture? My isosceles triangle. And here's the rectangle inscribed. And I know that this isosceles triangle has a base of 12 inches and a height of 9 inches. Thanks. We'll see how this relates to a cone inscribed in a, or thank you, a cylinder inscribed in a cone in a minute here. Thanks. So the problem with this is I don't know the dimensions of this rectangle. I want to find the dimensions that make it as big as possible. But I don't want to call it base and height because that's not going to be super useful. What I actually want to do, and this is true a lot of the time, is when you have a shape, whether it's a circle or a triangle or whatever, it usually makes sense to center it on the coordinate axis system. Meaning, I really want the origin to be in the middle of the bottom of this right here. So there's my origin. Here's my x-axis. Here's my y-axis. And specifically, these points I can know, and that's the point 0, 9. That's the point 6, 0. And this point here, I don't know what it is, right? I definitely want it to be touching the thing so I can use as much of the space as I have. But I'm going to call that x, y. Because it could be here, but it could be like way up here if I made a much taller and skinnier rectangle, it could look like that instead. Sorry, you guys can barely see that. All right, so we're trying to maximize the area of that rectangle, which, what's my equation for area? Right, and what's the height of this rectangle? Yeah, and what's the base? Well, it's not x, it's twice x. Because x is how far we are from the origin, so it's x over and y up. So the base is actually 2x, and the height is actually y. All right. It doesn't really matter if we maximize 2xy or xy. We're still going to get the same values for x and y in the end, but it's good to know what the base is, right? Our base is 2x. Our height is y. So if we're actually answering the question at the end, our answer should be whatever the base are, which is 2x, and the height is, which is y. Okay, so now we need, of course, a constraint, right? We've got this thing we want to maximize. There's too many variables. If there's 2 variables, we want just one. The constraining piece of information here is that this rectangle is being inscribed in the triangle, right? It can't be outside of it. Now, it could be smaller. Like you could make a rectangle like this. That's not going to have the most area. We need one where the corner of the rectangle is touching triangle. That's going to utilize the space the best. Meaning this point here has to be on that line. And we can definitely find the equation of that line. We've got some y equals mx plus b action happening here. Now, we are pretty fortunate in that we already know what the y-intercept is. It's 9. And the slope is pretty easy to figure out because from 0, 9 to 6, 0, we're going over 6 and down 9. So our slope is a rise of -9, a run of 6. -3/2. So our equation is y equal to -3/2 x plus 9. This is why we set it up the way. This is why I drew the triangle so that the base was centered on the origin so that I could write the equation in the line fairly straightforwardly. And now we're going to rewrite the area as a function of x, 2 times x times y. That's definitely something we're capable of maximizing. Let's multiply it out. 2x times negative 3 halves x is going to be negative 3x squared, and 2x plus 9 times 9 is 18x. Our derivative is going to be negative 6x plus 18. I set that equal to 0, and we're going to get x equal to 3. Does that give us a maximum? I don't know if you have to check this on your test, but I'm going to check it here. So the least x could be is 0, right? You couldn't have a value less than 0. The biggest x could be is 6. So we're kind of stuck between 0 and 6. And here's our critical value of 3. If I pick something smaller than 3, like 1, my derivative is definitely positive. Pick something bigger than 3, like 4, my derivative is definitely negative. So yeah, it's a maximum of 3. It's almost always going to be the thing they've asked you to find. And no one's going to ask you to minimize the area if you can't do that, unless they're real not nice. But I don't imagine your teachers would do that on purpose. Occasionally, maybe someone's made a mistake like that, but not usually. Are we done? Like, no. And if I've ever I've never asked that question. It's been yes. But maybe one time I will. It's just a trick. Like, make you guys think about it. But yeah, we're not done. We still have to find the other dimension. So I have that y equals negative 3 halves x plus 9. So y is going to be negative 3 halves times 3 plus 9, which is negative 9 halves plus 9, which is positive 9 halves. So my base is 2x, which is going to be 6 inches. My height is 9 halves, which is 4.5 inches. Now, the reason I started with this question is because when we talk about inscribing a cylinder in a cone, a lot of the work is the same. But before we move on, are there questions about anything we've done here? Yeah.
Why did you use y equals mx plus 3?
Well, so this point here, this corner of the rectangle had to be on this line. Thanks. So because of that, I know, like, so for example, you know, if x were 4, the y value has to be whatever the y value is on that line. So if x were 4, y would have to be negative 3 halves times 4 plus 9, which would be 3. But the whole point is that this line I can find using that. Now I could have done more. I could have done more kind of exposition there. I could have said, well, okay, the slope is going to be the difference in the y's over the difference in the x's. I found my slope that way. Just that. Am I answering your question? Okay, good. But basically, when you have shapes inscribed in other shapes, the whole kind of deal is like the corner of one shape has to kind of touch the other shape to get the maximum possible, either area or volume. And so typically, that point being on the line is what's giving us our constraint equation. All right, let's look at a very similar yet different example. So now we're going to ask same sort of question, except, sorry, apologies here. Find the dimensions of the largest cylinder by volume that can be inscribed in a cone of height 9 inches and base radius 6 inches. And although you could draw some three-dimensional-ish picture, I could draw, here's my cone. And here is the cylinder inscribed in it. It's actually not a super helpful picture to draw. What I really actually want is I want the two-dimensional projection of this picture onto the plane. So what I really want instead of a cone and a cylinder is a triangle and a rectangle. So I'm going to think of this as being like this. And then now I could label a couple things here, right? This, again, I'm centering on the x-axis. Sorry, centering on the xy coordinate plane, really. Well, since the radius of the cone is 6 inches, this point here is still 6, 0, and the height of the cone is 9 inches. The point there is still 0, 9. And the only real difference maybe here is that instead of calling this point x, y, I might call it r, comma, h. R for the radius of the cylinder, h for the height of the cylinder. But it's still the same sort of deal. So the difference in this problem is I'm not trying to maximize the area of the rectangle anymore. I'm trying to maximize the volume of the cylinder, which is going to be pi r squared h. But then I'm still going to have the exact same constraint as before. So my constraint is still the line y equals -3/2 x plus 9. Now I've done this one slightly differently to point out that that line is my constraint, right? That's that line right there. And the point r, comma, h should be on that line, meaning I'm going to plug in r for x and h for y. And this is good, or is it good? Is it good that I have h isolated and not r isolated? If I look back at my thing I want to maximize, it's definitely going to be easier to plug in for h. So yeah, I'm pleased that it's the h that is isolated and not the r. All right, let's plug in. So now our volume as a function of radius is going to be pi r squared times -3/2 r plus 9. So the thing we're going to maximize is definitely a different equation, right? Because we're talking about a different shape here. It's interesting. In the previous shape, essentially the base and the height kind of count the same, right? If you make one bigger and the other one smaller, each one only has the same amount of dimensionality. Whereas in this second shape, the base or the radius actually counts a lot more, because when we find the volume, it's pi times the radius squared times the height to the first. So we're going to see here that we actually want more base in this because it's giving you more of the volume. Let's simplify this a little bit. That's going to be -3/2 pi r cubed. I shouldn't really multiply the pi through, then that's silly. Let's keep the pi out and write it as pi times -3/2 r cubed plus 9r squared. That's a better choice. And then our derivative is going to be pi times, let's see, -9/2 r squared plus 18r. Set that equal to 0. All right, I'm going to solve this. I would probably factor out a 9/2 and an r. A 9/2, I don't know, 9/2 really, or just 9? I think just 9. I think whatever is easiest for you, really, is what I think. I'm going to factor out a 9r. My button's undone. Button that back up. Let's see here. So I factor out a 9 and an r. I'm left with a -1/2 r plus 2. Okay, that seems not terrible. then either r could equal 0, which we know is not what we want, or r could be, well, r is going to be 4. That seems like a much more reasonable answer. And then we should check to make sure it's a maximum. So if I look back at my derivative, with r being at the least 0, at the most 6, for the same reasons as before. If you pick something less than 4, like 1, my derivative is definitely going to be positive. If it's something bigger than 4, like 5, that part's going to be negative. So yeah, we have a maximum of 4. And then we find the other dimension. We go back to our height equation. Okay, if the height is negative 3 halves r plus 9, that's going to be negative 3 halves times 4 plus 9, which is negative 6 plus 9 is positive 3. All right. Not too terrible.
You know when we factor the 9 pi r outside?
Uh-huh.
I noticed in some problems, like they would like equal the 9 pi r to 0, right?
Sure.
And then the inside to 0. Would it mean that r is also has a possible value of 0?
Yes, and so I didn't show the work for that, but I definitely did do that. So I got r equals 0 here, and then I crossed it out because we know that a radius of 0 isn't going to give us the most volume, right? It's definitely going to give us 0 volume. But yeah, technically, right, we should be saying, okay, we can say each factor equal to 0. Okay, that's going to give us 0. Setting this factor equal to 0 gives us r equal to 4.
It's like important, like if the problem is like to take into account everything.
It's good to observe all of the critical values, even if they are not really sensible answers. Yeah.
Could you explain the constraint again?
Sure. So we actually got it from the previous problem, but I'm getting the constraint by saying that point there has to be on the line. That's the line of the triangle that the cone that we drew from the cone. And that line has an equation, y equals negative 3 halves x plus 9. And I'm getting that really, I'm getting it. So I think the easiest way to get it is to be like, well, from here to here, I can see that the slope is negative 9. Well, first of all, it's definitely negative, right? And then I know the rise is 9 and the run is 6. So it's a 9 over 6, but it's negative. So my slope is definitely negative 9/6. You can also do it like the longer way where you actually do 9 minus 0 over 0 minus 6. I'm just trying not to do all the work if I don't have to. I'm really trying to show you you don't have, right? I think it's perfectly reasonable for a student to be like, yeah, that slope is negative 9/6. No one's going to be like, oh, they didn't show their work on that. That's enough work.
So it's because that one point is on that line.
So one more time.
So it's because that one point is on that line.
Right, because if we're trying to maximize the volume of the cylinder and it's inscribed in the cone, it doesn't make sense for it not to touch the corner of it. And don't make the mistake I saw something made many years ago where they made the cone this way. It's really hard. It's a very hard problem to do if you try and think of the cone being sideways. It's not the right way to go. This is definitely the way that maximizes the volume. But yeah, whenever you're inscribing something, some point is touching some other point of the one shape to the other shape.
So the one that's on the outside doesn't matter. But when we look at the cone, this will become one with the sky.
Well, I mean, the cone, but the cone is this outer shape that's giving you that constraint, right? It's the fact that this point on the cylinder is touching the boundary of the cone. Or, and in drawn in 2 dimensions, this point on the rectangle is touching the boundary of the triangle. Let's do one more, at least one more anyway. So this one's maybe a little messier, but it's not terrible. Oh, should we do that one or that one? Let's see. Yeah, let's do the. let's do this one. So same sort of question. We want to maximize the volume of a cone inscribed in a sphere of radius 6. And of course, find the dimensions of said cone. Now, the three-dimensional drawing is not the helpful one, right? You can totally draw this sphere with a cone in it. Or can you? I don't know. Definitely not when you draw it poorly. It's not very helpful. But even if you draw it well, the three-dimensional drawing is not what you want. You want the 2D projection. So you don't want a cone inside a sphere. You want a triangle inside of a circle. So there's my triangle. Here's the center of the circle. And I know that this length here is the radius. That's 6. And do I need to know where my center is here? I'm not sure. I'm thinking about, no, I'm really not actually. I'm trying to think about what I want. Well, let's label some stuff. So I want to find I want to maximize the volume of the cone, which the volume of a cone formula is 1/3 pi r squared h. So here's my height. And here's my radius. And I need a constraint. All right, I've got the thing I want to maximize. I've labeled the things I need, but I need a way of relating them. And that's one way you could go. I hadn't thought about that, but that's all I was thinking. So, thoughts? That's not a bad idea. So I mean, the circumference would be 2 pi r, which would be 12 pi. But I'm not sure how that, yeah. Oh, it's actually one second. Be careful. This r and the radius of the sphere are different, right? This radius of the cone is not 6. It's not the same as the radius of the sphere.
I was going to say maybe a right triangle.
Definitely a right triangle to get. So here's the thing you want to think about. Where the inside shape touches the outside shape is kind of what's important. So this spot, and this spot are all kind of important. And it's often a good idea. So like when we inscribed, I know it's been a while, when we inscribed a rectangle and a semicircle, we drew the segment from the origin to the corner where they were connecting, where the rectangle was touching the semicircle. I'm gonna do the same thing here. I'm gonna draw that little segment there. What's the length of that segment? 6, it's the radius. Okay, I know this length here is the radius of the cone. And this length here, well, I know that the length, the total length up there is the height. So that length there is the height minus 6. And now we can totally use the Pythagorean theorem to relate those things. So the constraint for this particular problem is r squared plus h minus 6 squared equals 6 squared. All right. Here's a question I want you to think about for a moment. What should I solve for? Well, that's not even a good question. What should I solve for? We'll leave it at that. H is not a bad answer. It's going to get a little gross though, because I have to subtract r squared and square root both sides and then I have to square root both sides either way, unless I make an observation. I don't have just r up here, I have r squared. I could totally solve this for r squared and not even take the square root of both sides. That's what I'm going to do. So r squared is equal to 6 squared minus h minus 6 squared. And you don't need to square root both sides. Now, what I would do is I would simplify this, because this is going to be 36 minus h minus 6 squared is h squared minus 12h plus 36. And then the 36 is cancel. And you get r squared is negative h squared plus 12h, or 12h minus h squared. And that's exactly what we're going to do with it. So this is one of the few examples where you don't just solve for one of the variables. Typically, you solve for the square of it because it just makes the most sense. So plugging it back in, our volume as a function of height is going to be 1/3 pi times r squared, which is 12h. Whoops, that's a 12h minus h squared times h. I do want to point out, we're not squaring that, right? It's already squared right there. We should simplify. 1/3 pi times 12h squared minus h cubed. And now we'll differentiate to find the critical values. So the derivative here is 1/3 pi times 24h minus 3h squared. Factor out a 3h. I'm left with an 8 minus h. So either h equals 0, which again doesn't make sense for an answer, right? That's not going to have maximum volume, or the height equals 8. I know we haven't talked about it a lot, but in this question, what is the domain for the values of h? What's the smallest the height could be? 0. What's the biggest the height could be? I'm stuck in the circle, sorry, in the sphere. There's no way I could be more than whatever the diameter of the sphere is. So we are definitely limited to h being between 12 and 0. So when we think about, and again, you might not have to do this on your test, but when we think about if it's a maximum or not, picking something smaller than 8, like 1, and plugging into the derivative, we see it's definitely positive. Picking something larger than 8, like 9, plugging into the derivative, it's definitely negative. So it is increasing, decreasing. It is definitely a maximum at. And then to find now the r value here, so I did lie just a tiny bit. Eventually we will have to take a square root to find the r value. So it's definitely true that r squared is equal to 12h minus h squared. So 12 times 8 minus 8 squared. I would have probably factored out the 8 there. And said it's 8 times 12 minus 8, which is 8 times 4. That means r is going to be the square root of 32, which you could simplify to 4√2. That's how you can do a problem like this. This feels like a bit much for a test, but not totally unreasonable. I don't know. I mean, I don't know what he's going to ask on the test, right? Like, I would ask a question like this on the test. Maybe. Questions? What else do you want me to talk about in the last 20 minutes before? Oh, what time is your guys' test at? Okay, so you all should obviously leave at whatever moment you need to leave so that you can get there on time. If you need to leave now, that's really okay. I don't mind. I'm happy to stay and talk about things. So feel free to go whenever you need to go. You don't have to like say, James, I'm leaving now. You just walk, pick up and go. Let's see. Let's do a graphing problem. Seems like a good idea. A graphic. Which one should we do here? Sure. Let's try something like this. Let's say, yeah. So our function f of x is sure, x times the square root of 4 minus x squared. Whoops, sorry. Let's zoom back out. And we're going to graph it. We're going to find all the things, meaning first derivative stuff, second derivative stuff, everything. Starting this problem, it's always good to make note of a function if it has a limited domain. So in this particular problem, I would be like, oh, I'm not going to get very much graph because I need that to be greater than or equal to 0. You could say x squared has to be less than or equal to 4, which hopefully immediately conjures in your mind that x is between -2 and 2. Don't like that, you can also factor 2 minus x times 2 plus x has to be positive, which means x better not be too big or too small. X has to be between -2 and 2. Right, if x is 3, negative, positive. If x is -3, positive, negative. If x is in the middle, positive, positive. Good to go. So there's not going to be a whole lot of graph here. We'll just have to come from -2 to 2, and that's kind of it. You don't have to worry about any horizontal asymptotes if that's the case, because we can't go out to infinity or the negative infinity. And there's no vertical asymptotes to speak of because there's no division by 0 here. Or logarithms, right? Logarithms are the only way you get a vertical asymptote without dividing by 0. Kind of weird, right? Because every vertical asymptote you ever see really is like division by 0, except for a logarithm. A logarithm has a vertical asymptote, and there is no dividing by 0 involved there. It's other funky stuff. So I guess we should find the intercepts. Y-intercept, set x equal to 0. You're going to get y equal to 0. X-intercepts, set y equal to 0. We're obviously going to get x equal to 0, but we're also going to get x equal to what? X equals 0, and x could be either plus or minus 2. And now we need to start finding some derivative stuff. Take the first derivative. I would encourage you to imagine this is x times 4 minus x squared to the 1/2. Use the product rule and get 1 times 4 minus x squared to the 1/2 plus x times the derivative of that is 1/2 times 4 minus x squared to the minus 1/2 times a -2x. We do need to simplify this as much as possible to be able to find the critical values. There's a couple ways to do this. My preference, well, first, my preference is to cancel a 2 here and a 2 there. I'm going to write this, I'm going to rewrite this using roots. I'm going to write this as the square root of 4 minus x squared minus, there's a minus sign there, x times x is x squared divided by the square root of 4 minus x squared. And then the idea is that we're going to multiply this by square root of 4 minus x squared over square root of 4 minus x squared to get the common denominator. You can probably skip showing that work and get 4 minus x squared minus x squared all over the square root of 4 minus x squared, which is 4 minus 2x squared over the square root of 4 minus x squared. Factor out the 2. Okay. So what are my critical values? Well, what's making the numerator 0? Well, 2 minus x squared equals 0. I think we're going to get x equal to plus or minus the square root of 2, which is certainly in the domain, right? That's definitely between -2 and 2. And then where the denominator is 0, are those also critical values? I mean, there's no reason they shouldn't be, because they're real critical values, right? They're not those like pseudo ones I've talked about where they're not in the domain of the original function. These are totally in the domain of the original function. So I would say x equal to plus or minus 2 as well. All right. Continuing on. No, continuing on, we should make our first derivative sine chart. Let's go over here for that. Now we are limited, right? We can't go beyond -2 and 2. So we should not even think about anything out here or anything out here. But then we also have 0 and plus or minus root 2. So there's 0, there's minus root 2, there's plus root 2. So, all right, here's my derivative. Picking something close to 2, but not quite 2, like starting right over here. That part's going to be positive. No, that part's going to be negative, right? If I pick like 1.9, 1.9 squared is definitely bigger than 2. 2 minus that's going to be negative. The bottom should always be positive. It's going to be negative here. Something between 0 and root 2, like 1 is a good choice. 2 minus 1 is positive. Bottom's always positive. Then something like -1 still positive there. Still positive on the bottom. And then something like negative close to -2 is going to be negative on top, positive on the bottom. So my function, nice, is decreasing, increasing, increasing, decreasing. So we're expecting to have a relative minimum at x equal to negative root 2 and the relative maximum at x equal to positive root 2. And you could find the associated y values if you needed to. If you plug in root 2 back to the original, 4 minus 2 is 2. So you get root 2 times root 2, which is 2. Interesting. So f of root 2 is root 2 times root 2, which is 2. And f of negative root 2 is negative root 2 times root 2, which is negative 2. There's a lot of symmetry in this problem, right? This is definitely an odd function. If you plug in negative x for x, it becomes the negative of what it was. And at this point, although I might not be ready to graph it, I might draw myself a little graph just to kind of see, okay, here's what I think it's going to look like. I have so I know I've got a point at -2 and a point at 0, and a point at 2. And then how much is root 2? About? Definitely one of all the irrational numbers, it's the one people kind of expected to kind of know a little bit. It's about 1.4. It's about 1 point. It's like 1.41. This is the most I know. I think maybe the next one is 2. But as long as you know that root 2 is about 1.4, it's probably something you want to know. Meaning I know it's going to be almost 1.5 when I plot it. So I'm going to get a relative maximum when x is root 2 and the y value is 2. It'll be like right about there. And then when x is negative root 2 and y is -2. And at this point, I could probably do a decent job of drawing it because I have the sine chart. I know it's going to be decreasing, increasing, increasing, decreasing. And at 0, it should flatten out, right? Because the derivative at 0 is, oh no, 0, oh. I made a small mistake. It's not a huge deal, but I included 0 on my sine chart. And I really shouldn't have. Because 0 is not a critical point. It was on my intercepts. So let me explain the mistake I was about to make. I was about to draw my graph like this. Which is wrong. I had made the assumption incorrectly that 0 was a critical point where the derivative was equal to 0, and so the graph should be flattening out at the origin. But that's not right because 0 actually shouldn't have been included. So definitely a good reminder that you don't want to put 0 on there unless it's actually a critical value. It's really easy to want to include 0 because It's like the middle of the number line, but don't unless you need to. So it should be, it's probably gonna look more like this, actually. And so if I was guessing what's gonna happen with the second derivative, I'm guessing it's gonna be concave up from -2 to 0 and concave down from 0 to 2. Let's find out. Let's find out. Yeah, let's find out. So here's my first derivative. 4 minus 2x squared over 4 minus x squared to the 1/2 power. Writing it in the way that I know is going to be easiest to differentiate. And taking the second derivative. Again, do go if you need to go. Bottom, derivative at the top, minus the top, derivative at the bottom, okay, 1/2 times 4 minus x squared to the -1/2 times -2x, blah, over 4 minus x squared. Lovely, not. Cancel a 2 here. And at this point, instead of doing this whole common denominator thing, I would just factor stuff out. So from the top, I can factor out a 4 minus x squared to the -1/2, because that's the smaller power of the two, 1/2 and -1/2. I can also factor out an x. I'm left with a -4 here and a 4 minus x squared to the first. That's what's left from this first part here. And from the second part, I'm left with a 4 minus 2x squared. And I'm left with a -1. All divided by 4 minus x squared. I can say more about this factoring if you would like. Just to repeat here. So I factored out an x and a 4 minus x squared to the -1/2. So from this first piece, I was left with the -4 and the 4 minus x squared to the +1. From the second piece, I was left with the 4 minus 2x squared. And then that's gone, that's gone, that's gone. The x is gone, but the minus sign stuck around. So with a minus sign, which is plus. All right, simplifying. This comes down to the bottom. So you've got a 4 minus x squared to the 3/2 power. And then on top, you're left with x times, let's see what we've got here. We've got, oh, I remember. I've got worries because, well, you'll see why. So I've got a -16 plus 4x squared and then plus 4 minus 2x squared. So I've got x times -16 plus 4 is 12. And then 4x squared minus 2x squared is plus 2x squared. So setting this equal to 0 or undefined, I get x equal to 0, x equal to plus or minus 2, and then this part's never equal to 0, so it doesn't give us any extra critical values. So I was worried that this part here was going to give us more critical values. Let me point out, if instead this had been 12 minus 2x squared, we would have gotten x equal to plus or minus √6, which are also not critical values because they're not in the domain of the original function. So just be aware of something like that possibly happening. So looking at concavity, there's our critical values. That's the end of the road. Pick something larger than 0, like 1. Top is positive, bottom is positive. Yeah, positive, positive. So I'm concerned because it looked like my graph was concave down when I picked 1. It all seems right. It's always worrying when things don't match up with what you thought they should be. Oh, I see the mistake. That's a -16 plus 4. That is a -12. So I should actually point out, you do get x equal to plus or minus √6 as critical values, but they don't count because they're not in the domain. And then when you plug in 1, it is negative on top, positive on the bottom. And so it does actually look like what would that look like? All right. Now, question.
When you say it's not on top, and it's just not on the.
So one more time.
When you say that plus or minus square root of 3 is not on top, it's just not on top.
You mean plus or minus root 6?
Yeah.
Yeah, so plus or minus root 6, if we look back to the original function, it's not in the domain. Like, so if x is root 6, then you get 4 minus 6 square root gives you the negative in the square root. So yeah, so even though they look like they're critical values by setting this equal to 0, you don't actually get them because they make the original function undefined. All right, question, yeah.
How would we find the asymptotes?
There aren't any asymptotes.
If they were, how would we find them?
So the way you find the asymptotes, if there were asymptotes, so to find vertical asymptotes, you look for where the denominator is undefined or the denominator is 0 and the numerator is not. For horizontal asymptotes, usually I wait until I've done the sign chart for the first derivative. But what I typically do is you can also take the limit as x goes to infinity. So for example, if someone asked you to graph, say f of x equal to x e to the negative x, one way to graph that, or to find the horizontal asymptote, is to take the limit as x goes to infinity and see that it's this. X over e to the x, which goes to 0. But the other way to do this is when you find the first derivative, it's equal to e to the negative x plus x times e to the negative x times negative 1, which is e to the negative x times 1 minus x. You get a critical value of 1. Your derivative is negative here, positive here, so it's increasing, decreasing. But then what happens when you graph it is your intercept is here, and the function ends up being increasing before 1. Sorry, it's been a while, like it's increasing, it does something like this, yeah. It's increasing and then it's decreasing after, but it's decreasing and there's no x-intercept for it to cross, so it has to get closer and closer and closer to the y-axis, the x-axis there.
Yeah, thank you.
You're welcome.